Picture a universe in its infancy, a place of profound darkness and silence stretching across billions of light years. For nearly 100 million years after the Big Bang, not a single star twinkled in the void, no galaxies swirled, no planets formed. This was the cosmic Dark Ages, an era so mysterious that we have no direct light to study from it, only theories and whispers from the edges of time itself. Imagine standing at the edge of this vast, unlit cosmos, where the only things stirring were invisible forces and the faint echoes of creation, a period that holds answers to how everything we know came to be. During this time, the universe was a sea of neutral hydrogen gas, cooling and expanding in the aftermath of the Big Bang's fiery birth. Without stars or galaxies, space was a canvas of pure potential, waiting for anything to spark the dawn of light. What triggered that first brilliant moment when stars finally burst into being? How did darkness give way to light, and what hidden processes were at work in those shadowy eons? These questions lie at the heart of one of astronomy's greatest puzzles, a chapter in cosmic history that feels almost mythological in its obscurity, yet is crucial to understanding our very existence. Today, we're embarking on a journey to explore 30 astonishing theories about the universe's dark ages, ideas that range from the haunting presence of dark matter and primordial black holes to the possibility of exotic particles and cosmic strings influencing the birth of the first structures. Each theory offers a unique glimpse into what might have unfolded during this enigmatic time, and together they paint a picture of a universe far stranger and more wondrous than we ever imagined. So settle in and open your mind, because we're about to venture into the shadows of cosmic history, where the secrets of the universe's youth are waiting to be uncovered. Our journey into the cosmic Dark Ages begins with the most fundamental theory, one that paints the early universe not as a place of empty blackness, but as a realm filled with a profound, light-swallowing fog. This was not a fog of water vapor, but a dense, pervasive sea of neutral hydrogen gas. In the aftermath of the Big Bang, the entire cosmos was flooded with these simple atoms, each one a proton paired with an electron, and they were utterly neutral. They carried no electric charge. This state of neutrality is the key to understanding the great cosmic silence. Neutral hydrogen gas possesses a unique and powerful property. It is exceptionally efficient at absorbing high-energy ultraviolet light. So, even if the very first protostars had managed to flicker on during this era, their brilliant ultraviolet light would have been instantly snatched from the void, absorbed by this all-encompassing fog before it could travel even a short distance. The universe was effectively wrapped in a cosmic curtain, its earliest acts of creation playing out in complete secrecy. This period, where the fog reigned supreme, is what astronomers formally call the cosmic Dark Ages. It was a true universal dark age, a time before the first points of light could pierce the gloom and announce the dawn of structure. But how do we even begin to study an era that left no light for our telescopes to capture? The answer lies in a faint, specific signal that this very same hydrogen fog emitted. Every neutral hydrogen atom, even in the deepest cold of space, has a tiny magnetic orientation that can flip. When it does, it releases a whisper of radio energy at a very precise wavelength, 21 centimeters. This is known as the hydrogen line. Theoretically, this faint radio hum from the primordial fog holds an encoded map of the entire early universe, a fossil imprint of how matter was distributed before the first stars were born. Detecting this signal is one of the holy grails of modern cosmology. Projects like the Square Kilometre Array radio telescope are dedicated to this monumental task, aiming to tune into this ancient radio wave and translate its message, effectively allowing us to hear the Dark Ages and see the universe as it was before the dawn of light. The story of how this fog eventually lifted is just as crucial as understanding its existence. This immense sea of neutral hydrogen did not last forever. Its dissolution marks one of the most important transitions in cosmic history, an event called the Epoch of Reionization. The heroes of this story were the first generations of massive, furious stars and the earliest feeding black holes at the centers of budding galaxies. These objects poured immense amounts of energetic ultraviolet light and radiation back into the cosmic fog. This radiation was so powerful that it began to violently strip electrons away from the neutral hydrogen atoms, reionizing the gas and tearing apart the very fabric of the fog itself. Imagine tiny bubbles of clear, ionized plasma beginning to form around these first luminous objects, slowly expanding and eventually overlapping until the entire cosmic curtain was burned away. This was the end of the Dark Ages and the beginning of the transparent, star-filled universe we see today. The neutral hydrogen fog theory provides the essential foundation for this entire narrative, giving us the starting point, the blank, dark canvas upon which the entire history of light and life would eventually be painted. But if the neutral hydrogen fog made the universe a lightless void, what could possibly have pierced that perfect darkness? The answer might lie in one of the most exotic and fascinating theories to emerge from cosmology, the existence of primordial black holes. Unlike the stellar black holes we know today, which form from the collapse of massive stars, primordial black holes are thought to be a relic of the universe's very first moments. The idea is that in the incredible heat and density just after the Big Bang, random quantum fluctuations in the fabric of spacetime could have been magnified to macroscopic size, collapsing under their own gravity to form minuscule, incredibly dense knots. These wouldn't be the massive monsters of today's galaxies. Many theories suggest they could have been as small as an asteroid or even a pebble, yet containing the mass of an entire mountain, a mind-bending concept that speaks to the bizarre physics of the early cosmos. This theory radically challenges the traditional view of a completely uniform dark age. Instead of a homogeneous sea of gas, the universe might have been seeded with a hidden landscape of these invisible gravitational wells from the very beginning. Their presence would have had a profound and immediate effect. As these primordial black holes moved through the sea of neutral hydrogen, their immense gravity would have acted as cosmic anchors, pulling vast streams of gas toward them. This process of accretion, where matter spirals into a black hole, is notoriously violent and energetic. Even a small black hole consuming gas would heat that material to incredible temperatures, causing it to glow with X-rays and other forms of high-energy radiation long before the first true stars ever switched on. The Dark Ages, therefore, might not have been completely dark after all, but instead faintly illuminated by a sparse and ghostly array of these flickering primordial beacons. Perhaps the most revolutionary implication of this theory is the potential solution it offers to one of astronomy's greatest mysteries, the nature of dark matter. For decades, scientists have known that most of the matter in the universe is invisible, detectable only by its gravitational pull on galaxies. The leading candidate for this dark matter has been a hypothetical, slow-moving exotic particle, but despite massive efforts, none have been found. Primordial black holes present an elegant, albeit wild, alternative. What if dark matter isn't made of unknown particles at all, but is instead composed of these ancient black holes? They would be invisible, yet their collective gravity would perfectly explain the effects we see, effectively solving two cosmic puzzles with one incredible idea. The eventual fate of these tiny black holes adds another layer of wonder to the theory. According to Stephen Hawking's work, black holes are not entirely black. They slowly lose mass and evaporate over astronomical timescales through a process now known as Hawking radiation. For a very small primordial black hole, this evaporation would not be slow at all. It would be spectacular. In the final second of its life, such a black hole would release its entire remaining mass energy in a tremendous burst of radiation, a flash of gamma rays that could briefly outshine an entire galaxy. While most primordial black holes with significant mass would still exist today, the potential death throes of the smallest ones could have added unpredictable and brilliant flashes to the dark cosmic canvas, a final, explosive contribution to ending the universe's long, silent night. While the idea of primordial black holes offers a thrilling alternative, the leading theory for the unseen architecture of our universe remains the mysterious substance we call dark matter. This concept moves us from exotic objects to an invisible, pervasive component that is fundamental to our very existence. To truly grasp its role in ending the Dark Ages, we need to appreciate a critical cosmic imbalance. All the stars, galaxies, planets, and even the vast clouds of gas we can observe, everything made of the atoms that constitute you and me. This so-called normal or baryonic matter accounts for less than 5% of the universe's total content. Dark matter, which interacts through gravity but not through light, makes up over 25%. During the Dark Ages, this overwhelming majority of dark matter held the ultimate power to shape the future. Its influence began immediately after the Big Bang, while the intense radiation pressure of the early universe was smoothing out the distribution of normal matter, preventing it from clumping together. Dark matter was immune to this pressure. Since it doesn't interact with light, it was free to begin collapsing under its own gravity almost instantly. Tiny, random fluctuations in the density of the dark matter, quantum ripples stretched to cosmic size during inflation, began to amplify. Bit by bit, over millions of years, these slightly denser regions started to attract more dark matter, growing into vast, intricate, and invisible structures known as dark matter halos. Think of these halos not as solid objects, but as gigantic, diffuse spheres of gravitational influence, a cosmic framework or scaffolding woven from the fabric of gravity itself. This is where the fate of the neutral hydrogen gas was decided. This normal matter, THOUGH Chinese letter majority of the visible universe, was simply along for the ride, trapped in the gravitational wells carved out by the dark matter. The primordial sea of hydrogen gas began to slowly flow into these invisible halos, pooling at their centers. Without this pre-existing gravitational architecture, the gas would have had nowhere to go. Its own gravity was far too weak to overcome the universe's rapid expansion and begin forming complex structures on its own. The dark matter halos provided the essential gathering points, the gravitational seeds without which the first protogalaxies could never have coalesced. It was within these concentrated pools of hydrogen, deep inside the hearts of dark matter halos, that the gas could finally become dense enough to collapse under its own weight and ignite the very first stars. This process dramatically accelerated the timeline of cosmic dawn. Simulations of the early universe, some of the most complex computer models ever run, vividly demonstrate this dark matter influence. They show that in a hypothetical universe without dark matter, the formation of the first stars and galaxies would have been drastically delayed, perhaps by billions of years, leaving the cosmos in a prolonged and stagnant dark age. The presence of dark matter's gravitational scaffolding provided a shortcut, a faster path to complexity. The timing and the distribution of the first luminous objects were not random. They directly traced the underlying invisible web of dark matter. The end of the darkness was, therefore, not a uniform curtain lifting everywhere at once, but a gradual brightening as these islands of light flickered on, each one a beacon marking the location of a massive dark matter halo, finally bringing the universe's hidden skeleton into sharp relief. Yet for all their might and majesty, the first stars were destined for dramatically short lives, burning their nuclear fuel at a ferocious rate to counteract the immense gravitational pressure at their cores. These giants could only shine for a few million years, a mere blink in cosmic time. Their spectacular deaths were as influential as their births. A star hundreds of times more massive than our Sun would have ended its life in a cataclysm known as a pair instability supernova. an explosion so utterly violent and complete that it would tear the star apart, leaving behind no black hole or neutron star remnant. In this final, brilliant act, these first stars became the universe's first great alchemists. Within their furnaces, they forged the first heavy elements beyond hydrogen and helium, carbon, oxygen, nitrogen, and iron, and in their explosive deaths, they scattered these newly minted atoms like cosmic seeds across the primordial gas clouds. This pollution of the pristine environment was a pivotal turning point. It forever changed the composition of the universe, allowing future generations of smaller, longer-lived stars and eventually rocky planets like our own to form from this enriched material. The death of one population 3 star literally laid the groundwork for the complexity of life billions of years later. The elusive nature of these first stars makes finding direct evidence for them one of the most sought-after goals in all of astronomy. No telescope has ever definitively observed a population 3 star because their lifetimes were so brief, existing only in that remote era before most galaxies had even taken shape. Astronomers are therefore engaged in a kind of cosmic detective work, searching for their chemical fingerprints in the most ancient light we can see. The James Webb Space Telescope, with its unprecedented power to peer back towards the dawn of time, is designed to hunt for the telltale signs of these pioneers. It looks for galaxies with spectral light signatures that show a complete absence of heavy elements, a hallmark of a system still illuminated by its first generation of pristine stars. Alternatively, scientists are listening for the unique signature of a pair instability supernova, an explosion with a brightness and light curve unlike any other stellar death we see in the modern universe. Finding even one would be a monumental discovery, a direct window into the violent and brilliant processes that finally brought the cosmic dark ages to a close. Yet to truly understand the blueprint for all structure in the universe, we must venture back even further to a fleeting moment of unimaginable power that set the entire cosmic story in motion. This brings us to the profound and pivotal theory of cosmic inflation, an idea that suggests the universe's expansion didn't begin at a steady pace, but was instead launched by a period of hyper-fast exponential growth. In the tiniest fraction of a second after the Big Bang, a field of energy known as the inflaton field is thought to have pushed spacetime itself to expand faster than the speed of light, smoothing the cosmos to an incredible degree of uniformity and simultaneously magnifying minuscule quantum fluctuations to a cosmic scale. These random, microscopic ripples in the fabric of reality were stretched to macroscopic sizes, becoming the primordial density fluctuations that would eventually dictate where galaxies would form and where vast cosmic voids would remain. This inflationary burst didn't just create a smooth universe, it created a subtly textured one, imprinted with the faint gravitational potential for everything to come. The enduring evidence for this incredible event is written across the entire sky in the form of the cosmic microwave background, or CMB. This afterglow of the Big Bang, released when the universe was a mere 380,000 years old, is our deepest and oldest photograph of the cosmos. It shows a universe that is remarkably, but not perfectly, uniform. The tiny variations in temperature, warmer spots where matter was slightly denser, cooler spots where it was slightly more diffuse, are the direct imprint of those inflation-born fluctuations frozen in time. This snapshot is the ultimate cosmic Rosetta Stone, allowing scientists to decode the initial conditions of the universe. By meticulously studying the patterns and statistics of these hot and cold spots in the CMB, cosmologists can work backwards to test models of inflation and forwards to predict how these slight overdensities would behave over the ensuing eons. And it is here, in the quiet expanse of the Dark Ages, that the gravitational story truly begins. Following the release of the CMB, the universe entered its long period of darkness. But this was not a period of inactivity. Gravity was ceaselessly at work, acting on the blueprint provided by inflation. those regions of space that were ever so slightly denser, as seen in the warm spots of the CMB, possessed a tiny bit more gravitational pull than their surroundings. Over millions of years, this extra pull began to attract more and more of the surrounding dark matter and neutral hydrogen gas. The slightly dense regions became denser, slowly collapsing under their own gravity and beginning to form the very first gravitational wells. This process was incredibly slow and subtle at first, a gradual amplification of the cosmic whisper left by inflation. The Dark Ages were therefore the universe's great incubation period, where the seeds planted in the first fleeting instants were given the time and the silence they needed to slowly germinate in the dark. This theory provides the most fundamental and comprehensive narrative thread connecting the universe's birth to its eventual enlightenment. Cosmic inflation provides the initial conditions, the CMB provides the verifying snapshot, and gravity's patient work during the Dark Ages provides the mechanism. Without that initial inflationary period to create and amplify the density fluctuations, the universe would have remained almost perfectly smooth. There would have been no gravitational seeds for matter to gather around, no way for the gentle tug of gravity to overcome the relentless outward push of expansion. The Dark Ages might have stretched on indefinitely in a featureless sea of hydrogen. Instead, inflation gave the cosmos a head start, a preordained structure that allowed for the relatively rapid emergence of the first stars and galaxies once the conditions were right. It is a theory that beautifully links the quantum world of the impossibly small to the cosmic scale of galaxies and clusters, showing how the universe's largest structures have their origins in the smallest of quantum vibrations. While gravity and dark matter provided the primary architecture for the first structures, another invisible force might have been quietly at work in the background, subtly guiding the flow of matter: magnetism. The role of magnetic fields in the early universe is a fascinating and complex puzzle. We know that magnetic fields are woven throughout the modern cosmos, threading through galaxies and even the vast spaces between them, but their origins remain one of astronomy's great unsolved mysteries. Did they emerge later, generated by the churning motions of gas within galaxies and stars? Or could they have been present from the very beginning, a primordial force that helped sculpt the cosmos during its darkest hours? This theory proposes the latter, that magnetic fields are not a product of cosmic evolution but a foundational part of it, a subtle player in the drama of the Dark Ages. The concept of a primordial magnetic field pushes our understanding of physics to its limits. How could such a field be generated in the universe's first moments? One compelling idea involves cosmic phase transitions. Think of the early universe cooling from an incomprehensibly hot, dense state, much like steam condensing into water. As it cooled, it may have passed through several fundamental phase transitions where the forces of nature, which were once unified, split apart. These transitions could have created microscopic defects in the fabric of spacetime, cosmic strings, domain walls, or textures. The violent energy released as these defects settled could have generated turbulent plasmas, and where you have turbulent, charged plasma, you can generate magnetic fields through a process called a dynamo. In this scenario, the entire universe could have been imbued with a weak, large-scale magnetic field from its infancy, a fossil field that has been stretched and woven through the expanding cosmos ever since. If such a field existed, even an incredibly weak one, its influence on the neutral hydrogen gas of the Dark Ages could have been profound. Magnetic fields exert pressure and can resist the crushing force of gravity. As vast clouds of primordial gas began to flow into the gravitational wells of dark matter halos, a pervasive magnetic field would have acted like a delicate web within the cloud, providing a small but significant amount of support against collapse. This doesn't mean it would have stopped star formation entirely. Rather, it would have influenced how the gas fragmented. It could have encouraged the formation of more massive, dense clumps of gas or altered the efficiency with which a cloud could cool and condense. This subtle guidance might have directly impacted the size, distribution, and even the rotation of the very first protostars, making them different from what they would have been in a completely non-magnetic universe. The potential consequences ripple outward to one of the key events that ended the Dark Ages: reionization. The first stars were the primary drivers of reionization, but their ability to ionize the cosmic fog depended on their numbers, their masses, and their locations. If a primordial magnetic field altered the efficiency of star formation or the initial mass function of those first stars, it would have directly affected the timing and the morphology of reionization. Perhaps magnetic fields helped star formation happen more efficiently in certain filaments of the cosmic web, leading to an earlier and more patchy reionization process. Alternatively, they might have slightly suppressed fragmentation, leading to fewer, more massive stars that burned brighter and died faster, pouring radiation into the universe at an accelerated rate. A primordial magnetic field could be the unseen variable that explains why our models of reionization sometimes don't perfectly match the faint signals we're beginning to detect from that era. The challenge, of course, is proving it. How do you detect a magnetic field that permeated the entire universe over 13 billion years ago? Astronomers are pursuing two primary and incredibly faint signals. The first is its potential imprint on the cosmic microwave background. A universe-filling magnetic field would have affected how photons traveled in the early plasma, potentially leaving a distinct, twisted pattern in the polarization of the SIMB light, known as B-mode polarization. While the primary target for this search is the gravitational waves from inflation, a detectable signal could also be the unique fingerprint of a primordial field. The second avenue is the 21-centimeter signal from neutral hydrogen. A magnetic field would influence the temperature and density of the gas in specific ways, potentially leaving a statistical signature in the map of the Dark Ages that next-generation radio telescopes hope to create. Finding either of these signals would be a monumental breakthrough, not just confirming the existence of these ancient fields, but opening a completely new window into the physics of the universe's first second, a realm currently inaccessible to our particle accelerators, and one that holds the keys to understanding the very forces that shape our reality. But to truly appreciate the frozen echoes of the universe's earliest sound, we must journey back to a time of unimaginable heat and pressure, just a few 100,000 years after the Big Bang. This was the era of the primordial plasma, a searing, opaque soup where photons of light were hopelessly entangled with the protons and electrons that would later become hydrogen atoms. In this dense, pressurized environment, gravity was constantly trying to pull matter together into denser clumps, but there was a powerful opposing force: the intense radiation pressure from the blinding light. This created a titanic tug of war. A region of slightly denser plasma would begin to collapse under its own gravity, but as it compressed, the radiation pressure inside would skyrocket, causing the region to violently rebound and expand outward like a pressurized spring. This cycle of collapse and rebound set off powerful spherical sound waves, or acoustic oscillations, that rippled through the entire plasma universe at over half the speed of sound. This cosmic concert, however, had a final, abrupt encore, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The moment the cosmic microwave background was released, the music stopped. The photons, suddenly freed from their constant scattering with matter, streamed away, and the plasma instantly became a transparent gas. Without the radiation pressure to push back, the sound waves froze in their tracks. Each wave left behind a lasting imprint, a spherical shell of matter that had been pushed outward by the final, powerful rebound. Imagine countless bubbles, all of a very specific size, fossilized across the cosmos. This characteristic scale, the distance that sound could travel in the plasma before the universe became transparent, became a permanent standard ruler etched into the very distribution of matter. Throughout the long dark ages that followed, this frozen pattern was the hidden framework upon which the first structures began to form. The spherical shells left by the Barrian acoustic oscillations were regions of slightly higher density. As the invisible hand of gravity worked over millions of years to pull dark matter and gas into the first protogalaxies, it had a head start in these specific locations. Matter tended to cluster not just randomly, but with a subtle preference for this specific separation scale. While the Dark Ages are famously empty of light, they were quietly being structured by this acoustic memory, preordaining that when the first galaxies did eventually ignite, they would not be scattered randomly but would show a faint statistical tendency to be separated by this exact distance, an echo of a sound wave from a universe that was anything but silent. The incredible power of this theory lies in its use as a precision tool for cosmology, because we can calculate the exact size of this standard ruler based on the known physics of the primordial plasma. It gives us a fixed measuring stick against which we can gauge the expansion history of the entire universe. By mapping the positions of millions of galaxies in vast surveys, astronomers can look for this preferred scale in the clustering of galaxies. When they find it, they can measure how much the universe has stretched this ruler over billions of years. This provides one of the most robust and direct measurements of how dark energy has influenced the accelerating expansion of the cosmos. It acts as a cosmic dipstick, allowing us to test different models of dark energy and matter with extraordinary precision, all by listening to the faint, frozen echo of a sound wave that has been traveling through space-time since its very first moments. But as we contemplate the faint echoes of sound that structured the early cosmos, we must also consider the possibility of even more exotic defects in the fabric of spacetime itself. This brings us to one of the most speculative and captivating theories, the potential role of cosmic strings. Imagine the universe in its very first moments, a cauldron of inconceivable energy where the fundamental forces of nature were still unified. As this superheated cosmos expanded and cooled, it underwent a series of profound phase transitions, much like steam cooling and condensing into water. But in this cosmic condensation, the transition may not have been perfectly smooth everywhere. In some regions, the fields that govern the universe could have gotten stuck in a higher energy state, unable to smoothly transition to the new, cooler reality. The boundaries of these stuck regions could have collapsed into incredibly dense, incredibly thin filaments of pure energy, one-dimensional cracks in the fabric of spacetime known as cosmic strings. The properties of these hypothetical objects are truly mind-bending. A cosmic string would be thinner than a proton, yet it might possess an immense mass, with a single inch of its length potentially weighing as much as a mountain range. This creates a gravitational field unlike any planet or star. Because it is a linear defect, the gravity around a cosmic string would be intensely anisotropic, meaning it would pull more strongly along certain directions. Furthermore, spacetime around a string would be sharply curved. If you were to travel in a circle around one, you would find that the total distance is less than 2 pi times the radius, a bizarre geometric property that could theoretically allow for time travel if two strings were to move past each other at high speed. Most intriguingly, a cosmic string would not have ends. It would either form a closed loop or stretch across the entire universe, an infinite, vibrating filament of pure energy left over from creation. If such bizarre objects did form and persist into the Dark Ages, their impact would have been profound. Their immense gravitational pull would have acted as a powerful and immediate seed for structure formation. As a cosmic string moved through the sea of neutral hydrogen, it would have dragged a vast wake of dense matter behind it, much like a ship plowing through water creates a trailing wave. This process would have been incredibly efficient at concentrating gas, compressing it far more rapidly than the slow, gentle pull of dark matter alone could achieve. Regions crisscrossed by a network of these strings would have seen the first proto-galaxies form along these lines of intense density, like pearls on an invisible string. This offers a compelling alternative explanation for how the universe could have built its largest structures so quickly after the Big Bang, providing a potent catalyst to jump-start the end of the cosmic dark ages. The legacy of these cosmic strings might not be confined to the distant past. It could be detectable today. A vibrating loop of cosmic string would be a powerful source of gravitational waves, ripples in the fabric of space-time itself. Unlike the brief chirps from merging black holes detected by observatories like LIGO, a cosmic string would produce a continuous, stochastic background hum of gravitational waves across a wide range of frequencies. This would add a unique signature to the universe's gravitational wave background, a signal that next-generation space-based detectors are actively searching for. Furthermore, the bizarre lensing effect of a string could be spotted by telescopes. Because it warps space-time so sharply, a cosmic string moving between us and a distant galaxy would create a telltale effect, a perfectly duplicated image of that galaxy, split by a perfectly straight line with no distortion, a signature unlike the curved lensing caused by a spherical galaxy or black hole. While the search for these defects continues, the theory remains a powerful testament to the creativity of cosmology, demonstrating how the quest to understand the dark ages forces us to consider the most extreme and beautiful possibilities inherent in the universe's first moments. While we often speak of dark matter as a single, mysterious entity, the truth is cosmologists have long debated a fundamental question about its nature. Is it cold or is it warm? This distinction might sound trivial, but it has profound implications for how the cosmos emerged from its extended period of darkness. The leading model for decades has been cold dark matter, often abbreviated as CDM. This theory posits that dark matter particles are moving relatively slowly, a consequence of being cold and heavy. This sluggishness was its great strength in the early universe. Because cold dark matter particles are moving so slowly, they are easily captured by even the faintest gravitational tug. This allows them to clump together efficiently, starting with the tiniest of scales. Microscopic fluctuations can rapidly grow into tiny dark matter halos, which then merge to form larger and larger structures. This bottom-up scenario, where small structures form first and then hierarchically assemble into galaxies and clusters, has been the cornerstone of our understanding of cosmic evolution and matches many of the large-scale structures we observe in the universe today. The challenger to this established view is the theory of warm dark matter. Imagine a dark matter particle that is much lighter and faster, zipping through space at a significant fraction of the speed of light. This warmth changes everything about how it gathers. These faster-moving particles have enough energy to effectively resist being captured by the smallest gravitational wells. They would stream freely out of the tiniest density fluctuations, washing them out and preventing the formation of those minuscule primordial halos that are so crucial in the cold dark matter picture. In a warm dark matter universe, structure formation would follow a top-down, or at least a delayed bottom-up process. The first structures to form wouldn't be countless tiny halos, but instead larger, filamentary sheets of dark matter. Galaxies would then only begin to condense out of these larger structures at a later time. The cosmic dark ages in this scenario might have lasted longer, as the universe had to wait for these larger-scale gravitational potentials to form before gas could begin to pool and collapse into the first stars. How do we possibly choose between these two competing visions of our universe's hidden architecture? The answer lies in looking for the ghosts of structures that never were. Astronomers are using incredibly powerful supercomputer simulations to run the universe forward under both models. In a cold, dark matter cosmos, the prediction is that every large galaxy, like our own Milky Way, should be swarmed by thousands of small satellite dwarf galaxies, the leftover building blocks from its hierarchical assembly. While we do see some satellites, the number observed is significantly lower than what these CDM simulations predict. This missing satellites problem is one of the strongest hints that warm dark matter might have a role to play. A warmer particle would have suppressed the formation of precisely these smallest halos, naturally explaining why we don't see as many tiny galaxies as we might expect. The most exciting evidence, however, may come from tuning our instruments to the faint radio hum of the hydrogen line from the dark ages themselves. A 21-centimeter map of the early universe would be exquisitely sensitive to the distribution of matter on small scales. A signature of cold dark matter would show a cosmic web that is intricate and finely detailed, filled with tiny clumps and filaments. A map from a warm dark matter universe, by contrast, would appear noticeably smoother and more washed out on those smallest scales, lacking that fine-grained texture. By carefully analyzing this faint signal, projects like the Square Kilometre Array could effectively take a census of small-scale structure in the infant cosmos, providing a direct test to see if the dark matter is indeed cold, or if we need to warm up to a radically different idea of what makes up most of the matter in our universe. But to truly appreciate the frozen echoes of the universe's earliest sound, we must journey back to a time of unimaginable heat and pressure, just a few 100,000 years after the Big Bang. This was the era of the primordial plasma, a searing, opaque soup where photons of light were hopelessly entangled with the protons and electrons that would later become hydrogen atoms. In this dense, pressurized environment, gravity was constantly trying to pull matter together into denser clumps, but there was a powerful opposing force, the intense radiation pressure from the blinding light. This created a titanic tug of war. A region of slightly denser plasma would begin to collapse under its own gravity, but as it compressed, the radiation pressure inside would skyrocket, causing the region to violently rebound and expand outward like a pressurized spring. This cycle of collapse and rebound set off powerful spherical sound waves, or acoustic oscillations, that rippled through the entire plasma universe at over half the speed of sound. This cosmic concert, however, had a final, abrupt encore, when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms. The moment the cosmic microwave background was released, the music stopped. The photons, suddenly freed from their constant scattering with matter, streamed away, and the plasma instantly became a transparent gas. Without the radiation pressure to push back, the sound waves froze in their tracks. Each wave left behind a lasting imprint, a spherical shell of matter that had been pushed outward by the final, powerful rebound. Imagine countless bubbles, all of a very specific size, fossilized across the cosmos. This characteristic scale, the distance that sound could travel in the plasma before the universe became transparent, became a permanent standard ruler etched into the very distribution of matter. Throughout the long dark ages that followed, this frozen pattern was the hidden framework upon which the first structures began to form. The spherical shells left by the baryon acoustic oscillations were regions of slightly higher density. As the invisible hand of gravity worked over millions of years to pull dark matter and gas into the first protogalaxies, it had a head start in these specific locations. Matter tended to cluster not just randomly, but with a subtle preference for this specific separation scale. While the Dark Ages are famously empty of light, they were quietly being structured by this acoustic memory, preordaining that when the first galaxies did eventually ignite, they would not be scattered randomly but would show a faint statistical tendency to be separated by this exact distance, an echo of a sound wave from a universe that was anything but silent. The incredible power of this theory lies in its use as a precision tool for cosmology, because we can calculate the exact size of this standard ruler based on the known physics of the primordial plasma. It gives us a fixed measuring stick against which we can gauge the expansion history of the entire universe. By mapping the positions of millions of galaxies in vast surveys, Astronomers can look for this preferred scale in the clustering of galaxies. When they find it, they can measure how much the universe has stretched this ruler over billions of years. This provides one of the most robust and direct measurements of how dark energy has influenced the accelerating expansion of the cosmos. It acts as a cosmic dipstick, allowing us to test different models of dark energy and matter with extraordinary precision, all by listening to the faint, frozen echo of a sound wave that has been traveling through space-time since its very first moments. However, to truly understand the initial conditions that gravity worked with, we must question the very nature of the blueprint provided by inflation. The prevailing model assumes that the quantum fluctuations stretched across the cosmos were Gaussian. This is a statistical term meaning their distribution followed a very specific, symmetric pattern, like the random noise of static on a television screen. In a perfectly Gaussian universe, the density fluctuations are predictable. You won't find wildly extreme over-densities that are drastically more pronounced than the standard model allows for. But what if the universe's initial conditions weren't so perfectly random? This leads us to the compelling and complex theory of primordial non-Gaussianity. Non-Gaussianity proposes that the fluctuations imprinted by inflation contained correlations and patterns that deviated from this pure randomness. Instead of the gentle, predictable hills and valleys of a Gaussian landscape, the early universe might have been textured with unexpected features, perhaps a few exceptionally sharp, towering peaks amidst otherwise rolling plains or deep, concentrated valleys. These statistical anomalies would have been baked into the fabric of space-time from the very first instant, a subtle but profound signature of the physics that drove the inflationary epoch itself. Different models of inflation, such as those involving multiple fields or specific particle interactions, naturally predict different types and levels of these non-Gaussian correlations, making their search a direct test of what happened in that first fleeting fraction of a second. The impact of such a deviation during the Dark Ages would have been significant. Gravity is an amplifier. It takes small initial differences and makes them enormous over time. An underlying non-Gaussian distribution would have meant that the seeds for structure were not all created equal. Those rare, exceptionally high-density peaks predicted by some non-Gaussian models would have collapsed into the first massive dark matter halos much earlier than expected in a standard Gaussian scenario. The timeline for the formation of the very first stars and galaxies could have been dramatically accelerated, potentially shortening the Dark Ages by many millions of years. Conversely, certain types of negative non-Gaussianity could have suppressed the highest peaks, leading to a more uniform and delayed emergence of cosmic structure. The entire statistical profile of the cosmos, how galaxies cluster, the abundance of the largest clusters, and the emptiness of the great voids, would carry the indelible mark of these initial conditions. Thankfully, we are not left to merely speculate about these ancient statistical fingerprints. Scientists have two powerful observational tools to hunt for them. The first is the cosmic microwave background. The patterns of hot and cold spots in this ancient light are a direct snapshot of the density fluctuations. By conducting incredibly detailed statistical analyses of the CMB's temperature and polarization maps, cosmologists can search for the telltale signs of correlated fluctuations that shouldn't exist in a perfectly Gaussian field. Missions like Planck have placed tight constraints on non-Gaussianity, but future observatories will probe with even greater precision. The second tool is the large-scale structure of the universe itself. By creating vast three-dimensional maps of the distribution of galaxies and galaxy clusters, like those from the Sloan Digital Sky Survey, astronomers can look for statistical anomalies in the clustering. For instance, an excess of unexpectedly massive clusters at very high redshift, or a specific pattern in how galaxies group into triplets and quadruplets, could be the smoking gun for primordial non-Gaussianity. Discovering strong evidence for this would be a cosmological revolution. It would not only rule out the simplest models of inflation, but would open a direct window into the physics at energy scales 1,000,000,000,000 times higher than anything achievable in our particle colliders. It would tell us that the Dark Ages began with a far more interesting and complex set of initial conditions than we ever imagined, setting the stage for a more rapid and dramatic dawn of light. The search for these subtle statistical ghosts is a testament to how cosmologists use the universe itself as the ultimate laboratory, probing its deepest mysteries by reading the hidden patterns written in the oldest light and the largest structures. While the first stars were the brilliant beacons that ended the universal darkness, their spectacular deaths may have given rise to something even more consequential and enigmatic: the very first black holes. This theory delves into the origins of these gravitational monsters, suggesting they were born not in the mature cosmos we see today, but in the profound blackness of the Dark Ages, and that their formation was a pivotal event in shaping everything that followed. The prevailing idea is that the first generation of stars, the colossal population 3 giants, were the primary birthing grounds. These stars lived fast and died young, and for the most massive among them, those perhaps 250 times heavier than our Sun, their death was not a gentle fading but a total gravitational collapse. With such immense mass, the inward pull of gravity at the end of their brief lives would have been utterly unstoppable, overwhelming even the titanic force of a pair instability supernova. The entire stellar core would have crumpled in on itself, not exploding outwards but imploding catastrophically, disappearing from the visible universe and leaving behind a gravitational pit in spacetime, a black hole of perhaps several dozen solar masses. But there is an alternative, even more direct pathway to creation. Some cosmologists propose that the first black holes might not have needed stars at all. In the incredibly dense environment of the early universe, even before the first stars ignited, particularly massive primordial density fluctuations, those sharp peaks in the cosmic landscape we discussed, could have themselves collapsed directly under their own weight. If a cloud of hydrogen gas was dense and massive enough, and if it could somehow avoid fragmenting into smaller clumps that would form multiple stars, it could potentially bypass the star formation stage entirely and collapse directly into a black hole. This process would create what are known as direct collapse black holes, and they would be born behemoths with starting masses of tens or even hundreds of thousands of suns. These wouldn't be the stellar mass remnants of dead stars. They would be supermassive black holes from the moment of their birth, ready to anchor the centers of the first proto-galaxies. Regardless of how they formed, these first black holes would have immediately become the most dynamic and influential objects in their region of space. In the darkness, they were not dormant, they began to feast. Their immense gravity would have drawn in the vast reservoirs of neutral hydrogen gas that filled their dark matter halos. As this gas spiraled inward at near light speed, it would have compressed and heated to millions of degrees, forming a brilliant, whirling structure around the black hole called an accretion disk. This process of accretion is incredibly efficient at converting mass into energy, blazing with intense X-rays and ultraviolet radiation. A single, actively feeding primordial black hole could have outshone an entire galaxy of stars. This radiation would have played a dual role. It helped to heat and ionize the surrounding hydrogen fog, contributing to the process of reionization that was clearing the cosmic darkness, but it also may have exerted a form of feedback. The intense energy blasting out from the black hole could have actually pushed away nearby gas, potentially stifling further star formation in its immediate vicinity and self-regulating its own growth in a delicate cosmic dance. The legacy of these ancient objects is written in the heart of nearly every galaxy we see today. The supermassive black holes that power active galactic nuclei and lurk at the centers of galaxies like our own Milky Way, weighing in at millions or even billions of solar masses, pose a significant timing problem. How did they get so big so fast? The existence of billion solar mass black holes only a few 100 million years after the Big Bang is incredibly difficult to explain if they had to start from the remnant of a single dead star and slowly grow by accretion. The theory that they were seeded by massive direct collapse black holes or by the rapid merger of many early stellar mass black holes provides the most compelling solution to this cosmic puzzle. The black holes born in the Dark Ages were the seeds from which all subsequent galactic giants grew, their early formation providing the head start needed to achieve such staggering masses in such a short time. The most promising way to confirm these theories and truly probe this hidden chapter of history is not with light but with gravity itself. The mergers of these first black holes would have been the most violent events in the universe since the Big Bang, sending powerful ripples through the fabric of spacetime known as gravitational waves. Unlike the light from that era, which was absorbed by the hydrogen fog or stretched into invisibility, these gravitational waves would have traveled to us unimpeded, carrying a pristine record of their cataclysmic origins. Current observatories like LIGO and Virgo are detecting waves from black hole mergers in the nearby universe, but the next generation of instruments, like the space-based Laser Interferometer Space Antenna, or LISA, is designed to listen for the much lower frequency waves produced by the mergers of these primordial giants. Finding a population of merging black holes in the very early universe would be the ultimate validation, offering a direct, unedited audio recording from the end of the cosmic Dark Ages and finally revealing how the first shadows fell upon the newborn cosmos. While the immense gravitational pull of dark matter was busy sculpting the cosmos, another, far more mysterious force was also at work, one that operates in complete opposition to gravity's attractive nature. We are talking about dark energy, the enigmatic energy of empty space that is causing the expansion of our universe to accelerate. Today, dark energy is the dominant component of the cosmos, but its story during the Dark Ages is one of a quiet, almost imperceptible presence waiting in the wings. For billions of years after the Big Bang, the universe was a much denser place. Matter, both normal and dark, was packed more closely together, and its collective gravitational pull was strong enough to keep the cosmic expansion in check, even slowing it down over time. During this matter-dominated era, dark energy's repulsive effect was utterly negligible, like a tiny whisper drowned out by a roaring crowd. Its density remained constant while the density of matter plummeted as the universe expanded, meaning that for almost the entire duration of the Dark Ages, dark energy's influence on the growth of structure was virtually zero. However, the constancy of dark energy in our standard model is itself a profound assumption. The simplest and most accepted model describes it as the cosmological constant, a uniform energy density inherent to the vacuum of space that does not change over time. But what if that isn't the whole story? Some of the most intriguing theories in modern cosmology explore the possibility that dark energy is not constant at all, but is instead a dynamic field that could have evolved and changed its properties over the universe's history. These models, often called quintessence theories, propose that dark energy could have been stronger or weaker in the past, or could have even interacted with other components like dark matter. If dark energy had a slightly higher energy density or a different equation of state during those first few 100 million years, its impact would have been far from negligible. Even a small enhancement in its repulsive strength early on would have caused the universe to expand faster, stretching the fabric of spacetime more rapidly and making it just that much harder for gravity to pull matter together. The consequences of such an exotic early dark energy could have been profound for the timeline of cosmic dawn. A faster expansion rate during the Dark Ages would have diluted the primordial gas more quickly, making it harder for the tiny density fluctuations to grow. The gravitational tug of war between the inward pull of matter and the outward push of expansion would have been tipped slightly in favor of expansion. This could have delayed the collapse of the first gas clouds, potentially prolonging the Dark Ages by many millions of years. the first stars might have ignited later, and the process of reionization could have been a more drawn-out and less efficient affair. Alternatively, some very speculative models even allow for a brief early period where a dynamic dark energy field actually decayed, releasing energy and boosting the growth of structure. The range of possibilities highlights how much we still have to learn about this dominant component of our universe, and how its subtle behavior in the ancient past could have rewritten the entire schedule for the emergence of light. Understanding the true nature of dark energy's role is not just academic, it is crucial for building accurate models of the universe's evolution. Cosmologists precisely map the transition from the matter-dominated era to the dark energy-dominated era, which began roughly 5 billion years ago as a key benchmark. The timing of this transition is exquisitely sensitive to the properties of dark energy. By studying the large-scale structure of the universe and the remnants of the Dark Ages, like the 21-centimeter signal, scientists can look for any slight deviations from the predictions of the standard cosmological constant model. Finding evidence that structure formed either a little earlier or a little later than expected could be the first hint that dark energy is not constant, opening a window into physics beyond our current understanding and revealing that the force that now dominates our cosmic destiny also left its faint, ghostly signature on the universe's long, silent night. But as the cosmic fog began to lift, a major question arises. What exactly provided the immense power required to tear apart that pervasive sea of neutral hydrogen? This leads us to a pivotal debate at the heart of modern cosmology, a theory centered on identifying the primary engines of reionization. For the universe to transition from a dark, opaque state to the brilliant, transparent expanse we see today, something had to produce a staggering amount of high-energy ultraviolet radiation. The leading suspects in this cosmic mystery are the first generations of massive stars and the earliest accreting black holes, but determining which played the dominant role completely changes our narrative of how light finally conquered the darkness. The case for massive stars is a compelling one. The first stars, those population 3 behemoths, were not like the stars we see today. They were colossal, pure hydrogen factories burning at ferocious temperatures. Their immense size meant their surfaces were incredibly hot, causing them to emit most of their light in the high-energy ultraviolet range, precisely the type of radiation needed to knock electrons off neutral hydrogen atoms. Because these stars were so massive, they lived short, violent lives, meaning they poured this ionizing radiation into the cosmos in a relatively quick, brilliant burst. In this scenario, reionization would have been a process driven by countless points of starlight, each one creating a small, growing bubble of ionized plasma around it. As these bubbles expanded and began to overlap, the cosmic fog would have dissolved in a patchwork pattern, like holes appearing in a vast blanket until the entire thing disintegrated. On the other side of the argument are the early accreting black holes, particularly those shining as mini quasars. When a black hole actively feeds on surrounding gas, the material doesn't fall in directly. It forms a superheated accretion disk that can glow brighter than an entire galaxy. This process is incredibly efficient at generating not just ultraviolet light, but also even more energetic X-ray radiation. X-rays have a distinct advantage in the reionization process. They can travel much farther through the neutral hydrogen fog before being absorbed, allowing them to create larger ionized bubbles and heat the vast intergalactic medium more uniformly. A universe where black holes dominated reionization would have seen the fog clear in a different way, with fewer but larger ionized regions emanating from these brilliant central engines, potentially heating the gas so much that it actually suppressed later star formation in certain areas. The challenge for astronomers is that both processes were likely happening simultaneously. The true mystery is determining their relative contributions. This is where observations of the most distant objects in the universe become crucial. By studying high redshift galaxies with instruments like the James Webb Space Telescope, scientists can estimate how many massive stars these early systems contained and calculate their total output of ionizing photons. Conversely, by searching for similarly distant quasars, bright points of light powered by supermassive black holes, they can measure the power of these ancient engines. The current evidence points to a hybrid model. While massive stars probably provided the majority of the ionizing photons, early black holes may have played a critical role in preheating the intergalactic medium and creating the first large pathways for radiation to travel, making the overall process more efficient. The timing and pattern of this great transition offer the most telling clues. If reionization was a swift and uniform process, it would suggest a dominant, widespread source like stars. However, evidence suggests it was actually quite prolonged and inhomogeneous or patchy. The universe did not flip a switch from dark to light. The process likely took several 100 million years and occurred at different times in different places. This patchiness strongly supports the idea of a universe where isolated bubbles of ionized plasma slowly grew and merged. This fits a star-driven model where the first galaxies were the bubble sources. Yet, the discovery of fully ionized regions around incredibly distant quasars indicates that black holes were also powerful enough to create massive clearings on their own very early on. Ultimately, understanding this delicate balance between stars and black holes is key to mapping the universe's final emergence from its ancient dark age, revealing how two of the cosmos's most dramatic phenomena came together to illuminate all of creation. Yet for all our theorizing about the Dark Ages, we've been describing an era we've never directly seen, relying on the fossilized light of the CMB and the structures that came later to piece together the story. What if we could actually tune a radio to the frequency of the darkness itself? This brings us to one of the most anticipated and technologically ambitious theories in all of cosmology: the hunt for the 21-centimeter line signal from neutral hydrogen. This isn't just another idea, it's a potential portal, a direct channel that could allow us to listen to the symphony of the Dark Ages as it was actually happening. At the heart of this theory is a beautiful and subtle quantum process called the hyperfine transition. Each atom of neutral hydrogen in the primordial fog consists of a single proton and a single electron. Both of these particles act like tiny magnets, each with their own spin. Most of the time, the spins of the proton and electron are aligned, a slightly higher energy state. But very occasionally, about once every 10 million years for a given atom, the electron's spin will spontaneously flip, becoming anti-aligned with the proton. When this happens, the atom releases a tiny amount of energy in the form of a photon with a very specific wavelength, 21 centimeters, which places it in the radio band of the electromagnetic spectrum. In the modern universe, this signal is faint and difficult to detect from any one atom. But during the Dark Ages, the universe was filled with unimaginable quantities of neutral hydrogen. Collectively, this vast sea of atoms should have produced a faint but pervasive radio hum, a signature that has been traveling through the expanding universe for over 13 billion years, carrying an encoded snapshot of that entire era. Detecting this ancient radio whisper is the monumental goal of a new generation of radio telescopes. Projects like the Hydrogen Epoch of Reionization Array, or HERA, in South Africa, and the Future Square Kilometre Array, or SKA, are not your typical telescopes. They are vast fields of simple radio antennas spread across deserts to form a gigantic ear tuned to the cosmos. Their target is not the signal itself, but the subtle fluctuations within it. The 21-centimeter signal wouldn't be a uniform tone. Its intensity would vary slightly across the sky. These variations are the key. A slightly brighter patch of signal indicates a region where the hydrogen gas was a bit denser or a bit warmer. A fainter patch signifies a region that was more diffuse or cooler. By meticulously mapping these tiny differences in the signal's strength, astronomers could effectively create a three-dimensional tomographic map of the universe during the Dark Ages, revealing how matter was distributed long before the first stars switched on. The story this map could tell is unparalleled. In the early Dark Ages, the fluctuations in the 21-centimeter signal would primarily reflect the underlying distribution of dark matter, tracing the gravitational wells where matter was beginning to pool. This would give us our first direct view of the cosmic web in its infancy. As we move forward in time towards the epoch of reionization, the map would become even more dynamic. We would see the birth of the first stars and black holes not as points of light, but as growing bubbles of silence. That's because within these bubbles, the hydrogen has been ionized, the protons and electrons have been torn apart, and without neutral hydrogen atoms, there can be no 21-centimeter signal. A map of the reionization era would therefore show a cosmic Swiss cheese, with ever-expanding spheres of silence embedded within the faint radio glow of the remaining neutral fog, allowing us to watch in real time, billions of years later, as the lights literally turned on across the universe. The implications for testing fundamental physics are staggering. The statistics of the fluctuations in the 21-centimeter map would be exquisitely sensitive to the nature of dark matter. If dark matter is warm and suppresses small-scale structure, the map will appear smoother. If it is cold, it will show an intricate, fine-grained texture. It could even reveal the presence of exotic particles that interacted with and subtly heated the hydrogen gas. Furthermore, by observing how the signal changes with redshift, cosmologists can measure the expansion rate of the universe during the Dark Ages with phenomenal precision, providing an independent test for the nature of dark energy and potentially uncovering if its influence was different in the distant past. The 21-centimeter line is more than a signal. It is the universe's own recording of its most mysterious chapter, and we are finally building the technology to press play. Yet as we map the faint whispers of hydrogen and the gravitational echoes of the first structures, we must also account for a sea of ghostly particles that flooded the early cosmos, subtly shaping its evolution from the shadows. These are cosmic neutrinos, trillions of which pass through your body every second, utterly unnoticed. They are relic particles, frozen fossils left over from the first second after the Big Bang, and they played a quiet but crucial role during the universe's dark adolescence. To understand their influence, we need to appreciate their bizarre nature. Neutrinos are incredibly light, with masses so tiny they haven't been precisely measured, and they interact with normal matter only through the weak nuclear force and gravity, making them nearly invisible. In the hot, dense early universe, they were constantly slamming into other particles, but as the cosmos expanded and cooled, roughly 1 second after the Big Bang, they suddenly stopped interacting and began streaming freely across the universe. This moment, known as neutrino decoupling, created the cosmic neutrino background, a pervasive sea of these particles that has been flowing through everything ever since, a ghostly counterpart to the more famous cosmic microwave background. It is their unique combination of low mass and high speed that gave neutrinos their sculpting power during the Dark Ages. While dark matter was slowly collapsing to form the gravitational scaffolding for galaxies, this background of cosmic neutrinos was moving at a significant fraction of the speed of light. This high velocity gave them a property known as free streaming. Unlike cold, dark matter particles, which are slow and easily clumped together, fast-moving neutrinos have too much energy to be trapped by small gravitational wells. As they streamed freely across the expanding universe, they effectively washed out the smallest density fluctuations. Think of it like trying to build a delicate sandcastle too close to the shoreline. The incoming waves, the neutrinos, would constantly smooth over the finest details. This meant that the very smallest scales of the cosmic web, the tiniest potential dark matter halos, were suppressed. Neutrinos didn't stop structure from forming. they acted as a filter, ensuring that only the most substantial gravitational seeds, the larger over densities, could survive and eventually grow into the first galaxies. This smoothing effect has a direct and observable consequence for the universe we see today. In a cosmos where neutrinos have even a tiny amount of mass, their free streaming would have erased a specific population of the smallest, faintest dwarf galaxies that should otherwise orbit larger galaxies like our Milky Way. This provides a potential solution to the missing satellites problem we touched on earlier. The observed number of these tiny satellite galaxies aligns better with models that include neutrino mass than with those that assume massless neutrinos. It's a profound notion. The properties of these elusive, nearly massless particles from the dawn of time are written into the statistical distribution of the smallest galaxies in our cosmic neighborhood. The hunt for direct evidence of the cosmic neutrino background is one of the most challenging frontiers in cosmology. We cannot detect these relic neutrinos directly with current technology. Their energy is too low. Instead, we look for their subtle imprints on things we can see. The most promising place to search is in the cosmic microwave background. The presence of a sea of neutrinos in the early universe affected how the primordial plasma behaved before the CMB was released. Neutrinos contributed to the universe's energy density and influenced how quickly gravitational potentials could evolve, leaving a specific signature in the statistical patterns of the CMB's temperature and polarization fluctuations. By analyzing data from missions like Planck with incredible precision, cosmologists have already placed tight constraints on the total mass of all neutrino species, confirming they must have mass but are indeed very light. Another way to sense their presence is through the large-scale structure of the universe itself. The same smoothing effect that suppressed tiny galaxies also left a mark on the distribution of matter on the very largest scales. Detailed maps of millions of galaxies allow scientists to measure the strength of matter clustering. The observed suppression of clustering power on smaller scales provides indirect but strong evidence for the presence and mass of cosmic neutrinos. As we push further, aiming to map the neutral hydrogen of the dark ages with the next generation of radio telescopes, we may finally get a clear view of this neutrino smoothing effect in its active phase, watching as the ghostly sea of particles subtly shaped the canvas upon which the first stars would eventually shine. However, the entire narrative we've built so far of dark matter's invisible scaffolding guiding the formation of the cosmos rests on one fundamental assumption: that our understanding of gravity, as described by Einstein and Newton, is complete and universally correct. What if the problem isn't that we're missing most of the matter in the universe, but that we simply don't understand how gravity works on the grandest scales? This leads us to a truly radical set of theories that seek to rewrite the rules of physics itself, proposing that we can explain the cosmos without any dark matter at all by modifying our theory of gravity. The most prominent of these alternatives is known as modified Newtonian dynamics, or MUND. First proposed by physicist Mordechai Milgrom in the 1980s, MUND is based on a startlingly simple premise. It suggests that Newton's law of gravity, which works perfectly well in our solar system, breaks down in environments where the gravitational acceleration becomes incredibly weak, such as in the outer reaches of galaxies. Instead of the force of gravity continuing to decrease with the square of the distance, MUND proposes that it decreases more slowly following a different formula. This tiny tweak has a dramatic effect. It predicts that stars orbiting at the edge of a galaxy should move faster than standard Newtonian physics allows, which is exactly what we observe. In the standard model, this excess speed is explained by the gravitational pull of unseen dark matter. MUND achieves the same result by changing the rules of the game, not by adding new players. The implications of such a theory for the Dark Ages are profound and would completely rewrite the story of cosmic dawn. In a Mondian universe, there is no cold dark matter quietly collapsing over millions of years to form halos. Without that pre-existing gravitational architecture, the neutral hydrogen gas would have no ready-made wells to flow into. Structure formation would have to rely solely on the self-gravity of the gas itself and the modified force law. Proponents of MUND suggest that this altered gravity could actually enhance the growth of structure, making it easier for gas clouds to collapse without needing the extra pull from dark matter. This could potentially allow the first stars and galaxies to form even earlier than in the standard model, dramatically shortening the duration of the dark ages. The process of reionization might have begun sooner and progressed more rapidly, as these first luminous objects ignited in a universe where gravity gives a stronger assist to the collapse of material. The entire timeline from the Big Bang to the first light would be accelerated, challenging the need for a long, quiet incubation period dominated by invisible matter. MUND is not the only alternative gravity theory in play. Other, more complex frameworks have been developed, such as tensor vector scalar gravity, or TVS. This theory, developed by Jacob Bekenstein, is a relativistic extension of MUND, meaning it is designed to be compatible with Einstein's theory of general relativity, which governs the large-scale universe. TVS introduces additional fields, a vector field and a scalar field, that interact with gravity and modify its behavior on large scales. These fields effectively produce the same outcomes as MUND, but within a more complete cosmological framework. In a TVS universe, the patterns in the cosmic microwave background and the growth of large-scale structure would have to be explained through a complex interplay of these fields with normal matter, creating a cosmic web woven not from dark matter, but from the intricate dynamics of a modified gravitational force. The true test for these radical ideas lies in the detailed physics of the dark ages themselves. The 21-centimeter signal from neutral hydrogen is poised to be the ultimate arbiter in this debate. The fluctuations in this signal are a direct tracer of the distribution of matter. In the standard cold dark matter model, the pattern of these fluctuations is predicted to have a very specific, finely detailed texture, filled with tiny clumps and filaments corresponding to the smallest dark matter halos. A modified gravity theory like MUND or TVS would predict a very different pattern. Without swarms of low-mass dark matter halos, the distribution of hydrogen would be smoother on small scales. The upcoming maps from radio telescopes like the Square Kilometre Array will be sensitive enough to measure this small-scale structure. If they find the predicted fine-grained detail, it will be a powerful confirmation of the dark matter paradigm. If the map appears smoother, it could be the first strong evidence that we need to modify our understanding of gravity, not invent new forms of matter. This confrontation between dark matter and modified gravity is more than just a technical debate. It strikes at the heart of the scientific method. Both theories are trying to explain the same set of astronomical observations, but they start from completely different philosophical positions. One adds a vast, unseen component to the universe, while the other seeks to refine a fundamental force we thought we knew. The Dark Ages provide a unique laboratory to test these ideas because it was an era dominated by gravity alone, before the complicating effects of stars and galaxies. By looking back to that simple, dark time, we are conducting a pure test of gravity's true nature on a cosmic scale. The outcome will force us to either accept the existence of a shadow universe of dark matter or embark on a revolution in physics, rewriting the laws that have governed our understanding of the cosmos for centuries. Yet as we consider the fundamental rules that shaped our cosmos, we are compelled to ask an even grander question. What if the Dark Ages were not an inevitable chapter, but merely one possible outcome in a vast cosmic library of realities? This brings us to a theory that stretches the imagination to its absolute limit, suggesting that the long silence following the Big Bang might be a unique and finely tuned feature of our particular universe, one that may not be shared across a potentially infinite multiverse. The concept of a multiverse arises naturally from several cutting-edge theories in physics, most notably from certain models of cosmic inflation. The idea is that our universe, with its specific set of physical laws and constants, might be just one bubble in a frothing, eternal sea of spacetime, where countless other universes are continuously budding off, each with its own distinct properties. In some of these other universes, the laws of physics could be radically different, leading to cosmic histories that diverge wildly from our own. The duration and character of the Dark Ages in any given universe would be exquisitely sensitive to the precise values of these fundamental constants. Consider the strength of gravity governed by the gravitational constant, or the intensity of the nuclear forces that govern how atoms behave. In a universe where the gravitational constant was significantly stronger, the pull of matter would be more intense. This could cause the primordial gas to collapse into the first stars and galaxies much more rapidly, potentially shortening the Dark Ages to a fleeting moment or even skipping the era entirely. Conversely, a much weaker gravitational constant might mean gravity could never overcome the expansion of space, leaving the hydrogen gas forever diluted and the universe eternally dark and structureless, trapped in a permanent dark age with no hope for stars or life. The initial conditions set by inflation are another critical variable. Our universe appears to have had just the right amount of inflationary expansion to create a specific spectrum of density fluctuations, not too smooth, not too lumpy. But in another bubble universe, inflation might have ended sooner, leaving the cosmos far more smooth and uniform. Without significant density variations to act as gravitational seeds, the Dark Ages might stretch on for eons longer as matter struggles to clump together. Alternatively, if another universe had undergone far more violent inflation, it could have been left with extremely sharp density peaks. These regions might collapse directly into enormous black holes almost instantly, creating a universe dominated by darkness of a different kind, a landscape of gravitational abysses with no stable galaxies or stars in between. Perhaps the most profound implication of this theory is its connection to the concept of fine-tuning for life, often discussed in the context of the anthropic principle. The fact that our universe had a Dark Ages period that was neither too short nor too long seems crucial for our existence. A drastically shortened Dark Age might not allow enough time for the cosmic ingredients to cool and settle into the right structures, potentially leading to a chaotic and unstable universe. An excessively prolonged Dark Age, on the other hand, could mean that stars form too slowly and sporadically, not producing enough heavy elements to forge planets and ultimately living organisms. Our particular journey from darkness to light, with its specific timeline, appears to be a necessary prelude to a universe that can become aware of itself. The cosmic Dark Ages, therefore, might be more than just a mysterious era in our past. They could be a signature of a universe whose fundamental rules are precisely calibrated to allow for the eventual emergence of complexity and consciousness, a single note in a much larger and possibly infinite cosmic symphony. But to truly appreciate the origins of the cosmic structures that began their growth in the Dark Ages, we must venture back to a moment of incomprehensible energy, to the very birth of spacetime itself. This brings us to a cornerstone of modern cosmology, the profound theory that the largest structures in our universe, from vast galaxy clusters to the tiniest dwarf galaxies, owe their existence to the ghostly tremors of the quantum realm. The story begins in the first minuscule fraction of a second after the Big Bang, during the hypothesized period of cosmic inflation. In this era of hyper-fast expansion, the universe was a seething sea of energy, a place where the very concepts of empty space and particles were blurred by the rules of quantum mechanics. On these unimaginably small scales, empty space is never truly empty. It is a turbulent foam where pairs of virtual particles and antiparticles constantly flicker into and out of existence, borrowing energy from the vacuum for a fleeting moment before annihilating and returning it. These are quantum fluctuations, temporary bubbles of something emerging from nothing, governed by the uncertain and probabilistic nature of reality at its most fundamental level. The genius of the inflationary model is how it takes these ephemeral quantum events and magnifies them to a cosmic scale. As the fabric of space-time expanded faster than the speed of light during inflation, these microscopic quantum fluctuations in the inflatoned field, the energy field driving the expansion, were stretched across vast distances. What was once a tiny, random ripple on a quantum sea became a macroscopic variation in the density of the universe, a region where a quantum fluctuation had created a tiny bit more energy would, after inflation, become a region with a slightly higher density of matter and energy. A region with a tiny bit less energy would become a slightly under-dense void. This process provided the universe with its initial conditions, a barely perceptible pattern of hills and valleys in the cosmic landscape. This pattern is not just a theoretical idea, we have a photograph of it, the cosmic microwave background, that ancient light from when the universe was only 380,000 years old, shows us these density variations as tiny temperature differences. The warm spots are the slightly denser regions that would one day become galaxies. The Dark Ages were the critical incubation period where this quantum blueprint was transformed into a gravitational reality. After the release of the CMB, the universe was plunged into darkness, but it was far from inactive. It was during this long, quiet epoch that gravity began its patient work on the seeds planted by those quantum fluctuations. Each slightly denser region possessed a tiny bit more gravitational pull than its surroundings. Over millions of years, this extra attraction acted like a cosmic magnet, slowly and inexorably pulling in more dark matter and neutral hydrogen gas. The quantum hills grew into gravitational mountains. The process was one of gravitational instability, where a small initial overdensity becomes unstable to its own gravity and begins to collapse. The Dark Ages provided the perfect environment for this amplification, a universe free from the disruptive pressure of radiation, where the gentle, persistent force of gravity could work unimpeded to sculpt the cosmos. The faint whisper of a quantum fluctuation eventually grew into the deep gravitational well of a protogalaxy. This theory provides the most breathtaking connection in all of physics, linking the impossibly small world of quantum mechanics to the impossibly large scale of the cosmic web. The statistical nature of quantum fluctuations directly predicts the statistical nature of the universe's large-scale structure. The random, Gaussian pattern of the quantum foam is why galaxies are not distributed evenly, but are instead grouped into clusters, filaments, and walls surrounding immense voids. The specific spectrum of these initial fluctuations, predicted by different models of inflation, determines the precise details of how matter clusters together. By studying the distribution of galaxies across billions of light years, cosmologists are effectively conducting an archaeological dig into the quantum properties of the infant universe, testing physics at energy scales far beyond the reach of any particle accelerator on Earth. The enduring power of this idea is that it makes a clear and testable prediction. If all structure truly grew from quantum fluctuations, then the initial patterns should be random and follow the statistical rules of quantum mechanics. This is precisely what observations of the CMB and galaxy surveys have found, providing strong support for the inflationary paradigm. The Dark Ages, therefore, were not a featureless pause but a dynamic era of translation, where the universe quietly and meticulously converted the cryptic language of quantum probability into the clear, gravitational script of stars, galaxies, and ultimately, us. Every structure we see today is a monument to a quantum event that occurred in the first trillionth of a second of time, a permanent testament to the profound connection between the microcosm and the macrocosm. While the first stars and black holes poured radiation into the cosmos, another, more subtle form of energy may have been at work, seeping into the neutral fog and carving out the earliest pockets of ionization. This theory shifts our focus from the brilliant light of massive objects to the realm of high-energy particle physics, suggesting that cosmic rays played a crucial and overlooked role in the narrative of the Dark Ages. Cosmic rays are not rays of light at all, but are instead atomic nuclei, mostly protons, that have been accelerated to nearly the speed of light. They are the universe's natural particle accelerators, and their origin in the early universe could have provided a potent, penetrating force that helped prepare the cosmic stage for the main act of reionization. The most likely source for these first cosmic rays would have been the spectacular deaths of the very first stars. When a population 3 star reached the end of its brief, furious life and exploded as a supernova, the expanding shockwave from the blast would have acted as a powerful particle accelerator. This shockwave would have raced through the surrounding interstellar medium, and protons and other atomic nuclei caught in its path could have been swept up and accelerated to relativistic speeds. Unlike ultraviolet photons, which are easily absorbed by the dense hydrogen fog, these high-energy protons are electrically charged and can travel much greater distances through a neutral medium. They would have penetrated deep into the heart of the neutral hydrogen clouds, delivering their energy far from their point of origin and influencing regions that ultraviolet light from the central supernova remnant could not yet reach. The impact of these early cosmic rays would have been twofold, affecting both the chemistry and the ionization state of the primordial gas. When a high-energy cosmic ray proton collided with a neutral hydrogen atom, it could have knocked the electron clean off, ionizing the atom and creating a free proton and a free electron. This process is far less efficient than photoionization from ultraviolet light, but its reach was potentially far greater, allowing for the creation of faint, widespread, and isolated pockets of ionized plasma long before the intense radiation from stars and quasars became dominant. Furthermore, cosmic rays play a vital role in chemistry. In the simple hydrogen-helium universe, the primary molecule was hydrogen deuteride, but cosmic rays could have catalyzed the formation of molecular hydrogen by ionizing hydrogen atoms, which then allowed them to react more readily with other atoms. Since molecular hydrogen is a very effective coolant, helping gas clouds to shed heat and collapse to form stars, this indirect effect could have actually accelerated the formation of the second generation of stars, creating a positive feedback loop that brought about the end of the Dark Ages more quickly. This theory adds a fascinating layer of complexity to our models of this epoch. It suggests that the universe's transition from darkness to light was not a simple, monolithic process driven solely by starlight, but a more intricate tapestry woven from multiple different threads of physics. The ionization of the cosmos likely occurred through a combination of ultraviolet photons, X-rays from early black holes, and the penetrating power of cosmic rays, each contributing in a different way and on a different scale. Cosmic rays would have created a faint, pervasive background of ionization, a precursor to the more dramatic and complete clearing that was to come. This cosmic ray pre-ionization would have made the intergalactic medium slightly more conductive and perhaps slightly warmer, subtly changing the conditions under which the first galaxies assembled and the first stars ignited. Testing this idea requires looking for unique signatures in the most ancient light we can detect. The 21-centimeter signal from neutral hydrogen is once again a key tool. The presence of a significant population of early cosmic rays would have subtly heated the hydrogen gas in a specific way, imprinting a particular statistical pattern on the fluctuations of the 21-centimeter signal that radio telescopes like the Square Kilometre Array hope to detect. Additionally, the very high energy gamma rays produced when cosmic rays interact with other matter could leave a faint, diffuse background glow that might be distinguishable from other sources. While incredibly challenging to detect, finding evidence for this particle-based influence would complete our picture of the Dark Ages, revealing a universe where not just light, but also the invisible rain of atomic nuclei helped to write the final chapter of cosmic darkness. But as we trace the origins of the elemental building blocks forged in the first moments of creation, we encounter a cosmic mystery that has puzzled astronomers for decades, a tiny discrepancy with enormous implications known as the primordial lithium problem. This puzzle takes us back to a time even before the Dark Ages, to the first 3 minutes after the Big Bang, a period known as Big Bang nucleosynthesis. In that incredible heat, the universe acted as a colossal nuclear furnace, fusing the primordial protons and neutrons into the first atomic nuclei. About 75% hydrogen, 25% helium, and trace amounts of deuterium, helium-3, and lithium-7. For the most part, the predictions from this process match our observations of the oldest stars in the universe with stunning accuracy, except for lithium. The amount of lithium-7 we observe in these ancient stellar atmospheres is only about 1/3 of what our models of Big Bang nucleosynthesis predict should be there. It's as if the universe's recipe for this element has a missing ingredient or a hidden instruction we haven't deciphered, a tiny crack in our otherwise robust understanding of the cosmos's first moments. This discrepancy is far more than a minor accounting error. It hints at the possibility of entirely new physics operating in the primordial universe, processes that may have continued to influence the cosmic environment throughout the ensuing Dark Ages. One compelling set of theories suggests that the lithium was indeed created in the predicted amounts, but was then destroyed or transformed by something we haven't yet accounted for. A leading candidate involves exotic particles that may have been present and active in the early universe. For instance, certain theoretical particles, such as those predicted by some supersymmetry models, could have decayed during or after Big Bang nucleosynthesis. The energetic products of these decays might have collided with the newly forged lithium nuclei, breaking them apart into smaller elements like helium and reducing the overall abundance. Alternatively, these particles could have subtly altered the nuclear reaction rates themselves, changing the efficiency with which protons and neutrons fused into lithium and throwing off the final tally. The implications of this lithium shortfall extend directly into the Dark Ages. The chemical composition of the primordial gas cloud is not a trivial detail. It is a fundamental property that governed how the first structures formed. Lithium, though rare, plays a specific role in astrophysical processes. It acts as a coolant. In the cold, dense molecular clouds that were collapsing to form the first stars, the presence of lithium atoms can help the gas shed thermal energy more efficiently, allowing it to condense and fragment. If the lithium abundance was significantly lower than we think, the gas chemistry during the Dark Ages would have been different. The cooling would have been less efficient, potentially altering the fragmentation of the first gas clouds and changing the initial mass function of the very first stars. Perhaps the first stars were, on average, more massive in a lithium-poor universe, which would have meant they burned hotter, died younger, and poured more ionizing radiation into the cosmos, potentially accelerating the end of the Dark Ages. A tiny change in the initial ingredients could have rippled forward through time to reshape the entire timeline of cosmic dawn. Solving the primordial lithium problem is therefore a key to unlocking a more complete picture of the universe's infancy. It forces us to question whether our understanding of nuclear physics in those first 3 minutes is truly complete, or if we are missing a piece of the puzzle that involves particles or forces beyond the standard model. The Dark Ages, often seen as a simple, passive period, might have been the stage where the aftermath of this earlier anomaly played out, with the altered chemistry of the gas quietly influencing the formation of the first luminous objects. By studying the atmospheres of the most ancient stars with powerful telescopes and cross-checking the results with increasingly precise models of Big Bang nucleosynthesis, cosmologists are inching closer to an answer. Cracking this case would not only resolve a long-standing tension in our models, but could open a window into physics at energy scales so high they can only be probed by looking back to the very beginning of everything. While the search for WIMP has captivated physicists for decades, another, more elusive candidate has been steadily gaining traction, a particle so subtle and strange that it challenges our very notion of what dark matter could be. This is the theory of action dark matter, a concept that emerges not from cosmology, but from the enigmatic world of quantum mechanics. The action was first proposed in the 1970s to solve a completely different, deeply technical problem in particle physics known as the strong CP problem. In essence, the theory of quantum chromodynamics, which governs the strong nuclear force, seems to allow for certain symmetry violations that we simply do not observe in nature. The universe appears to have a surprising preference for symmetry in this specific interaction, and the most elegant solution is the existence of a new, very light particle that suppresses these effects. This particle was named the action, and while it was invented for one reason, it soon became clear it had a stunning secondary property. Under the right conditions, it could be produced in enormous quantities in the early universe and could, in fact, be the dark matter we've been searching for all along. What makes actions such a compelling alternative to WIMP is their profoundly different nature. They are predicted to be incredibly light, potentially billions of times less massive than even an electron, and they would interact with normal matter only very weakly and rarely. But their most mesmerizing quality is their quantum behavior. Because they are so light and cold, actions wouldn't behave like a swarm of discrete particles. Instead, they are theoretically governed by the rules of quantum wave mechanics. This means that across the vast expanse of the cosmos, a vast collection of actions could act in unison like a single, coherent wave. This collective behavior could allow them to condense into exotic, large-scale quantum states known as Bose-Einstein condensates. Imagine the dark matter halo of a galaxy not as a cloud of individual particles, but as a gigantic, singular quantum object, a ghostly wave function stretching across thousands of light years, its behavior dictated by the same physics that describes atoms in a lab. This isn't just a different type of matter, it's matter behaving in a way we've never directly observed on a cosmic scale. This quantum wave nature could have left a unique fingerprint on the formation of the first structures during the Dark Ages. In the standard cold dark matter model, the smallest structures form first, but if dark matter is made of actions, their wave-like properties introduce a fascinating new scale. There is a minimum size below which these quantum waves cannot be compressed due to a principle known as quantum pressure. This means that action dark matter would naturally suppress the formation of the very smallest dark matter halos. This could elegantly solve the missing satellites problem, the puzzling observation that we see fewer small dwarf galaxies orbiting the Milky Way than our simulations predict. The action wave wouldn't allow such tiny structures to form in the first place, smoothing out the cosmic web on the smallest scales and potentially leaving a much cleaner match with what we actually observe in the night sky. Beyond their gravitational influence, actions could have also provided a faint, ethereal light in the darkness. Some theoretical models suggest that actions are not entirely stable. Over astronomical timescales, they could spontaneously decay, converting into pairs of photons. This process would produce a very specific, low-energy radio signal that would permeate the entire universe. During the long dark ages, this decay radiation would have created an incredibly faint universal glow, a background light completely separate from the cosmic microwave background. This subtle illumination wouldn't have been enough to ionize the hydrogen fog, but it could have provided a gentle, pervasive source of heating for the primordial gas. Even a tiny amount of extra heat can affect how gas collapses to form stars, potentially altering the efficiency of the first star formation and subtly influencing the timeline of reionization. The Dark Ages might not have been a period of perfect thermodynamic cold. They could have been gently warmed by the slow, radiant decay of the universe's most abundant but invisible component. The hunt for these phantom particles is underway in laboratories around the world, using technology that borders on the magical. Unlike WIMP detectors buried deep underground, action hunters use powerful magnetic fields and ultra-sensitive radio receivers. The Action Dark Matter Experiment, or ADMX, is the flagship of this effort. It operates on a beautifully simple principle. If actions exist and they are everywhere, then inside a strong magnetic field, they should occasionally convert into detectable microwave photons. The experiment is essentially the world's most sensitive radio, meticulously tuning through millions of frequencies, listening for the faint whisper of an action converting into a photon. It's a painstaking process, like searching for one specific radio station in a universe of static, not knowing its exact frequency. A detection would be a monumental breakthrough, not only revealing the identity of dark matter, but also validating a sophisticated solution to a fundamental problem in particle physics, all while opening an entirely new window into the quantum underpinnings of the cosmic dark ages. But to ignite the universe's very first star, the primordial gas needed to accomplish one critical feat. It had to cool down. This brings us to a deceptively simple yet profoundly important theory centered on the formation of the first molecules. In the vast, near-perfect vacuum of the Dark Ages, the sea of neutral hydrogen was incredibly cold, but not cold enough for a cloud of gas to collapse under its own gravity and ignite nuclear fusion. It must be able to shed energy to contract and grow denser. Atomic hydrogen on its own is notoriously inefficient at this. Its methods of cooling are limited, especially in the absence of heavier elements. The hero of this story, the catalyst that made star formation possible, was a simple pairing of two hydrogen atoms, molecular hydrogen or H2. The formation of this molecule in the pristine early universe was a complex and delicate dance. Without any dust grains or pre-existing complex matter to act as a catalyst, the reactions had to occur directly in the gas phase. The primary pathway is thought to have begun with the tiny fraction of hydrogen atoms that were ionized, left over from the Big Bang. A free electron could collide with a neutral hydrogen atom, creating a negatively charged ion. This ion could then attract a second hydrogen atom, and when the electron was knocked loose again, it left behind a bound molecule of H2. It was a slow, inefficient process, but over millions of years, even this faint trickle of molecular hydrogen accumulation was enough to begin changing the fate of the cosmos. The power of molecular hydrogen lies in its structure. Unlike a single atom, a molecule can vibrate and rotate. These internal motions provide new ways for the gas to lose energy. When a cloud of gas undergoes gravitational compression, it heats up. This heat creates pressure that fights against further collapse. But if the gas contains H2 molecules, that heat energy can be converted into rotational energy and then radiated away as infrared light. This allows the cloud to cool, the pressure to drop, and the collapse to continue. Molecular hydrogen acted as the universe's first radiator, a vital cooling system that allowed the first dense, massive star-forming cores to condense out of the otherwise stable primordial fog. Theoretical models show that the rate of H2 formation was the master regulator for the dawn of the first stars. Slight variations in this rate, influenced by factors like the ambient radiation field or the density of the gas, would have had a dramatic impact on the timeline of cosmic dawn. In regions where molecular hydrogen formed more efficiently, gas clouds could cool and collapse faster, leading to an earlier ignition of the first stars. In other, more diffuse regions, the process would have been delayed. This variation could be a key reason why reionization didn't happen everywhere at once, but instead progressed as a patchy, gradual process with brilliant bubbles of light switching on at different times across the dark cosmic canvas. Understanding the precise physics of these first molecules is not just an academic exercise. It is the cornerstone of accurately simulating the end of the Dark Ages. Modern supercomputer models of the early universe must include complex chemical networks that track the formation and destruction of H2. The results are incredibly sensitive to these rates. Get the chemistry wrong, and your simulated universe might form its first stars far too early or too late, or create stars with the wrong masses, which in turn affects how much ionizing radiation they produce. The humble hydrogen molecule, a simple pairing of the two most abundant atoms, emerges as a critical character in the story, a tiny chemical key that unlocked the potential for all the light and structure that was to follow. However, this monumental transition from darkness to light was not a simple, uniform event like a sunrise washing over a smooth landscape. Instead, the latest theories suggest the dawn was a chaotic and patchy affair, a process astronomers call inhomogeneous reionization. Imagine a vast, dark forest where the first campfires are lit not at the same time, but randomly and far apart. Each fire creates a small bubble of light and warmth, and only as these bubbles slowly grow and merge does the entire forest become illuminated. This is precisely how our universe is thought to have emerged from its long cosmic night. The very first stars and black holes did not appear evenly spread throughout space. They formed in the densest knots of the cosmic web, where dark matter had pulled together the most gas. This meant that the powerful radiation they emitted began to ionize the hydrogen fog only in their immediate surroundings, creating isolated bubbles of clear, transparent plasma. The size and growth of these bubbles were dictated by the nature of their power sources. A brilliant but short-lived massive star might create a relatively small ionized sphere before it died. In contrast, a voracious, feeding supermassive black hole could sustain its output for much longer, blasting out radiation capable of carving a truly enormous cavity in the neutral fog. The expansion of each bubble was also a race against time and space. The intense ultraviolet radiation at the bubble's edge worked to ionize new territory, but the surrounding neutral hydrogen constantly fought back, trying to recombine and swallow the light. The rate of expansion depended on how many ionizing photons the central source could produce and how quickly the surrounding gas could recombine. This created a complex, evolving mosaic across the cosmos, with brilliant islands of light separated by vast continents of lingering darkness. This patchiness is not just a historical curiosity, it is the key to understanding the entire reionization process. The pattern of these bubbles encodes vital information about the first luminous objects. For instance, if the bubbles we detect are generally small, it would suggest that the dominant sources of ionizing radiation were numerous but relatively low-powered, like populations of massive stars. If we find evidence for a few extremely large bubbles very early on, it would be a strong indicator that supermassive black holes were already active and powerful enough to dominate their regions of space. By carefully mapping the size, distribution, and evolution of these ionized regions, we can effectively take a census of the universe's first engines of light and determine what they were and how they worked. Our most powerful tool for creating this map is once again the 21-centimeter radio signal from neutral hydrogen. As these ionized bubbles grew, they were not sources of this signal. They were voids of silence within the constant radio hum of the neutral fog. A radio telescope tuned to this frequency would therefore not see a uniform glow, but a spectacular and dynamic Swiss cheese pattern. The colder, denser neutral regions would appear brighter in the 21-centimeter line, while the hot, ionized bubbles would appear as dark splotches. By observing this signal at different frequencies which correspond to different distances and thus different times, we could watch a time-lapse movie of these dark splotches growing, merging, and eventually filling the entire screen, documenting the universe's final victory over darkness. This intricate patchwork also had a profound effect on the growth of the next generation of structures. The intense radiation pouring out of these early bubbles didn't just ionize atoms, it also heated the surrounding gas to temperatures of tens of thousands of degrees. This created a form of cosmic feedback. Outside an ionized bubble, the gas was cold, neutral, and primed for future star formation. But right at the edge, the gas was heated and pressurized, making it much more difficult for it to collapse and form new stars. This meant that the very act of reionization could actually stifle further creation in its immediate vicinity, effectively self-regulating the process. The first galaxies to form, therefore, had a profound influence on their neighbors, their light carving out not only spheres of transparency, but also creating heated galactic halos that shaped the destiny of emerging structures for millions of years to come. The precise moment when the first starlight pierced the universal darkness remains one of the most active debates in modern cosmology. This event, poetically termed the cosmic dawn, wasn't a single flip of a switch but a gradual, flickering process, and its exact timing holds the key to understanding the fundamental physics that governed the early universe. Different theoretical models paint strikingly different pictures of this dawn. Some simulations, which incorporate standard cold dark matter and efficient gas cooling, suggest that the very first stars could have ignited astonishingly early, perhaps only 100 million years after the Big Bang. In this scenario, the Dark Ages were a relatively brief interlude, with structure formation progressing rapidly once the initial conditions were set by inflation. Other models, however, introduce factors that could have significantly delayed this awakening. For instance, if the dark matter was slightly warm, its free streaming motion would have suppressed the formation of the smallest halos, pushing the timeline for the first star formation back by many millions of years. Similarly, early feedback mechanisms, such as the faint but pervasive X-ray heating from the first accreting black holes or the photoevaporation of gas clouds by the first massive stars, could have created a self-regulating cycle. This cycle would periodically heat and disrupt nearby star-forming regions, effectively putting a temporary break on the process and stretching out the dawn into a more prolonged twilight. The quest to pin down this timeline is not merely an academic exercise in cosmic history. It is a direct test of our most fundamental theories. The duration of the Dark Ages is exquisitely sensitive to the properties of dark matter and the initial density fluctuations from inflation. A universe that emerged from darkness very quickly strongly supports the cold dark matter model and a specific spectrum of primordial fluctuations. A universe that remained dark for a longer period points toward more exotic physics, such as warm dark matter or a dynamic form of dark energy that influenced early expansion rates. Essentially, by measuring how long it took for the first stars to form, we are conducting a grand experiment on the nature of the universe's most mysterious components. The darkness wasn't just an empty void, it was a duration, a measurable period of time whose length encodes the very rules of reality. Fortunately, astronomers are not left to rely on theory alone. They have two powerful observational tools to directly probe this elusive era. The first is the hunt for high redshift galaxies with instruments like the James Webb Space Telescope. By pushing to ever greater distances and looking further back in time, Webb is searching for the most ancient stellar systems ever formed. Finding a galaxy that existed when the universe was only 200 million years old would support an early dawn model, while a conspicuous absence of galaxies at that epoch would suggest a more delayed timeline. The light from these galaxies, their spectra in particular, can also reveal their chemical composition. The very first galaxies should be devoid of heavy elements, and finding such pristine systems helps pinpoint the era when star formation was just beginning. The second, and perhaps most promising, tool is the detection of the 21-centimeter hydrogen signal from the Dark Ages themselves. This faint radio hum is a direct probe of the neutral gas that filled the universe before reionization. As the first stars and galaxies turned on, they would have created growing bubbles of ionized plasma within this neutral fog. A radio telescope capable of mapping the 21-centimeter signal across different frequencies which correspond to different cosmic times would allow us to create a three-dimensional movie of reionization. We could literally watch as these bubbles of ionization emerge, grow, and merge. The timing of the very first bubbles and the rate at which they expand would provide a direct, unambiguous clock for the cosmic dawn, finally revealing how long the universe waited in silence and what ultimately brought that silence to a brilliant and definitive end. Imagine a scene from the earliest chapters of the cosmos, a single colossal star, hundreds of times the mass of our sun, burning with a furious blue-white intensity in an otherwise endless sea of pristine darkness. For a few million years, it is the sole beacon in its corner of the universe, a titan pouring forth a torrent of ultraviolet radiation. Then, in a final, cataclysmic act, it explodes, scouring its surroundings with the energy of a billion suns. This isn't just a spectacular death, it is a transformative event that forever changes the rules of the game. The theory of feedback from the first stars proposes that these pioneering luminaries were not passive actors but active shapers of their environment, their lives and deaths creating a complex web of consequences that either promoted or stifled the birth of future generations, directly influencing how quickly light could conquer the cosmic dark. This feedback operated through two powerful and opposing channels. The first is radiative feedback. The intense ultraviolet light from a massive population 3-star didn't just travel outward, it hammered against the surrounding reservoir of cold, neutral hydrogen gas. This radiation had enough energy to violently strip electrons from atoms, ionizing the gas and heating it to extreme temperatures. Imagine this process creating a growing, hot bubble of ionized plasma around the star. While this was crucial for the larger process of reionization, it had a local suppressive effect. For a new star to form, a cloud of cold, dense gas must be able to collapse under its own gravity. The intense heat and pressure from a nearby stellar neighbor made this impossible. The gas became too hot and energetic to condense, effectively putting a halt to star formation in that immediate vicinity. The very first star in a region could therefore sterilize its local neighborhood, preventing the rapid emergence of a cluster of stars and instead ensuring that future generations would have to form at a much greater distance where the disruptive influence had faded. The second channel is mechanical feedback, delivered by the supernova explosion that marked the star's inevitable demise. When these behemoths died, they did so in spectacular fashion, likely as pair instability supernova that left no remnant behind. The expanding shockwave from such an explosion plowed through the interstellar medium with unimaginable force. In some cases, this blast wave could compress nearby clouds of cold, neutral hydrogen that had somehow survived the star's radiative onslaught. By squeezing this gas to much higher densities, the shockwave could actually trigger a new wave of gravitational collapse and star formation, a process known as supernova-induced star formation. This is how the death of one star could give birth to many, seeding the next generation far from the site of the original explosion. However, this same shockwave could also have a destructive effect. If it blasted through a region that was already on the verge of forming stars, it could tear the delicate gas clouds apart, dispersing their material and delaying collapse for millions of years. The feedback from a single star was therefore a double-edged sword, a cosmic cycle of creation and destruction that governed the rhythm of star birth in the infant universe. The cumulative effect of this feedback, happening again and again across the cosmos, was to regulate the pace of reionization and structure growth. It ensured that the end of the Dark Ages was not a simple, uniform transition but a complex and patchy process. Ionized bubbles grew not just from the continuous output of stars, but in fits and starts as new stars were born from the ashes of the old, only to then heat their own surroundings and suppress their neighbors. This feedback loop helps explain why reionization took several 100 million years to complete. It wasn't a steady march, but a chaotic dance of progress and setback. Furthermore, it solves a key problem in our simulations of the early universe. Without incorporating these feedback mechanisms, models tend to produce far too many small, faint galaxies and convert the neutral hydrogen to ionized plasma far too quickly. The inclusion of feedback from the first stars provides the necessary throttle, slowing down the process to match the gradual, inhomogeneous reionization that our observations of the cosmic microwave background and distant quasars suggest actually occurred. The first stars, therefore, were not just the bringers of light, they were the universe's first architects of regulation, their brilliant lives and violent deaths writing the rules that would govern the construction of everything that followed. Yet among the brilliant giants and voracious black holes, we must not overlook the potential contribution of the universe's most numerous and humble structures, the dwarf galaxies. These faint, diffuse collections of stars are far more than just minor players in the modern cosmos. Theories suggest they may have been the very first galaxies to ignite, and their collective power might have been the steady, pervasive force that finally burned away the cosmic fog. Unlike the massive spiral and elliptical galaxies that dominate our night sky, dwarf galaxies are tiny, often containing only a few million or billion stars compared to the hundreds of billions in a galaxy like our Milky Way. But in the early universe, this small size was their greatest advantage. The first dark matter halos to collapse and begin pulling in neutral hydrogen gas were the smallest ones. They reached the critical density for star formation long before the larger, more massive structures that would eventually become galactic titans. This means the very first flickers of starlight in the cosmos likely came not from grand spiral disks, but from countless tiny, faint dwarf galaxies scattered like isolated villages across the vast dark landscape. The central question surrounding these pioneers is whether they could have produced enough ionizing radiation to make a real difference. A single dwarf galaxy, with its limited reservoir of gas and stars, would have been a feeble source compared to a brilliant quasar or a massive starburst galaxy. But their power lay in their overwhelming numbers. The early universe could have been teeming with these small systems, a cosmic population where dwarfs outnumbered larger galaxies by 1,000 to 1. While each one contributed only a small amount of ultraviolet light, their combined output could have been immense, like a billion candles collectively producing as much light as a single spotlight. Furthermore, the very nature of these small galaxies might have made them more efficient at releasing their radiation into intergalactic space. Massive galaxies tend to hold onto their gas tightly. Much of the ionizing radiation produced by their stars can be absorbed by dense clouds of gas and dust within the galaxy itself before it ever escapes to affect the wider cosmos. Dwarf galaxies, with their weaker gravity and thinner gas, could have been leaky, allowing a much higher fraction of their precious ionizing photons to stream out into the void and chip away at the neutral hydrogen fog. This theory of a dwarf-dominated reionization paints a very different picture of cosmic dawn. Instead of a few brilliant beacons punching through the darkness, it suggests a gradual brightening from a countless array of tiny points of light. The process would have been more uniform and steady, with ionization bubbles forming everywhere at once and slowly merging. This contrasts with the model where a few brilliant quasars create huge, isolated bubbles very early on. The timeline of reionization, therefore, holds the key to distinguishing between these scenarios. A process that was drawn out and highly inhomogeneous or patchy supports a significant role for numerous small sources like dwarf galaxies. If reionization was instead quick and more uniform, it would point toward fewer, more powerful engines being the primary drivers. This is where our most powerful new window to the past, the James Webb Space Telescope, becomes indispensable. Webb is uniquely equipped to hunt for these ancient dwarf galaxies. Its incredible sensitivity allows it to detect the faint infrared glow of stars in these tiny, distant systems that were previously invisible to us. By conducting deep field surveys, Webb is not just looking for the occasional brilliant galaxy. It is taking a census of the entire population of early galaxies, especially the faint, numerous dwarfs. By counting them and measuring their properties, astronomers can finally calculate their total contribution to the ultraviolet background that powered reionization. Early results are already revealing a surprising abundance of small, faint galaxies at very high redshifts, suggesting that their role was indeed significant and may force us to revise our models of how light first filled the universe. These tiny, ancient galaxies are no longer just footnotes in cosmic history. They are emerging as potential heroes of the story, the collective force whose countless small fires finally ended the universe's long, deep night. While the initial density fluctuations from inflation provided the blueprint for all cosmic structure, not every ripple in the primordial pond was destined to grow into a galaxy. There was a fundamental limit, a minimum size below which gravity simply couldn't assemble matter, and this threshold was set by a subtle but powerful process known as silk damping. To understand this, we must return to the universe's fiery youth before the Dark Ages, to the time of the last scattering when the cosmic microwave background was released. In that primordial plasma, photons of light and charged particles like protons and electrons were locked in a constant, frenzied dance. Photons would zip through the plasma, constantly scattering off the free electrons, effectively making the entire universe a thick, opaque fog where light couldn't travel freely. This endless scattering had a profound effect on the tiny density fluctuations we've discussed. Imagine a very small, slightly denser region of this plasma. Gravity is trying to pull the matter in this region closer together, to make it even denser and begin the process of forming a structure. However, the photons trapped within this dense knot are under high pressure, and they desperately want to diffuse outward to escape into the less dense surrounding areas. On very large scales, gravity wins this tug of war, but on small scales, the photons have the upper hand. They act like a powerful smoothing iron, scattering out of the overdense region and carrying energy and matter with them, effectively washing out the tiny fluctuation before gravity can amplify it. This process of photon diffusion, which erases small-scale inhomogeneities, is what we call silk damping, named after the astrophysicist Joseph Silk who first described it. The result of this cosmic ironing was the establishment of a specific minimum size for cosmic structures, known as the silk mass or silk scale. This is the smallest mass of dark matter that could possibly collapse to form one of the first gravitational seeds, a sort of cosmic lower limit. Any primordial fluctuation smaller than this scale was effectively erased from the universe's blueprint, smoothed into non-existence by the relentless pressure of light. This scale isn't arbitrary. It can be precisely calculated from the known physics of the primordial plasma, and it gives cosmologists a crucial prediction. It tells us that there should be a fundamental cut-off in the spectrum of structures, meaning there should be no dark matter halos below a certain mass that formed during the Dark Ages. This prediction has immense consequences for the story of the first stars and galaxies. The initial mass function of the very first stars, the distribution of their sizes, was directly influenced by the amount of gas that could cool and collapse within these smallest possible dark matter halos. The silk scale sets the mass of the very smallest gas clouds that could have survived this smoothing process, which in turn influences whether the first stars tended to be true behemoths or if a population of smaller stars could have formed alongside them. If the smallest halos were prevented from forming, it might have skewed the first generation of stars toward larger average masses, creating a population of brilliant, short-lived giants that would have profoundly influenced the early stages of reionization. The enduring power of the silk damping theory is that it leaves a clear, observable signature that we can still detect today, etched into the cosmic microwave background. The process of photon diffusion doesn't just erase fluctuations, it also slightly heats the plasma in a specific way. This imparts a distinct statistical pattern to the tiny temperature variations in the CMB, particularly suppressing the power of fluctuations on very small angular scales. By meticulously analyzing the CMB with instruments like the Planck satellite, cosmologists can measure this suppression and confirm the predictions of the silk damping scale with remarkable precision. This observation provides a stunning verification of our understanding of the universe's physics just moments before it plunged into the darkness, offering a final snapshot of the initial conditions that gravity would work with for the next several 100 million years. The silence of the Dark Ages was not imposed upon a blank slate, but on a canvas that had already been prepped and primed by the relentless, smoothing pressure of light. And now we arrive at perhaps the most speculative and mind-expanding theory of all, a concept that pushes the boundaries of cosmology into the realm of profound possibility. Could the cosmic Dark Ages have hosted intelligence? The idea of pre-galactic civilizations existing in that profound blackness, long before our sun or even our galaxy had fully formed, is certainly not a mainstream scientific position, but it serves as a powerful thought experiment that forces us to confront the sheer vastness of what we do not know. This era spanned nearly 100 million years, a period of time more than twice the entire history of life on Earth, from the first single-celled organisms to modern humanity. To assume that this immense stretch of time was devoid of any interesting activity beyond the slow collapse of gas clouds is, in a way, its own form of assumption. The universe had the raw materials: hydrogen, helium, gravity, and time, and the parameters of physics were set. If the conditions for complex chemistry and perhaps even biology could have arisen in some exotic environment, the Dark Ages would have provided a stable, quiet backdrop utterly unlike any other period in cosmic history, free from the sterilizing violence of frequent supernova that would come to plague later epochs of star formation. What might such a civilization even look like, and how could it sustain itself? Without conventional stars as a stable, long-term energy source, a truly ancient intelligence would have had to be incredibly innovative. One hypothetical energy source could have been the annihilation of dark matter, if it turns out to be a particle that can interact with itself and release energy. A species might learn to gather and concentrate these particles, fueling their society with a power source utterly invisible to us. Alternatively, they could have harnessed the gravitational energy of primordial black holes or the latent heat from the residual warmth of the Big Bang itself. Their existence might not have been planet-bound in any way we recognize. Their habitat could have been vast, free-floating structures in the deep void, or even networks built within the cool, dense clouds of molecular hydrogen that were the only nurseries of their time. Their entire mode of existence, their technology, and their perception of reality would be so fundamentally alien that we might not even recognize signs of their activity as artificial. The most compelling aspect of this theory is not its likelihood, but the challenge it presents to our methods of detection. If such a civilization did rise and fall in the deep dark, what lasting signature could it possibly leave behind that we might detect over 13 billion years later? Some have suggested that an advanced intelligence might have attempted large-scale astrophysical engineering, perhaps to alter the course of star formation in their vicinity or to communicate their presence. Such activities could have imprinted anomalies on the distribution of matter that we might see in the faint statistical patterns of the 21-centimeter signal or in the detailed structure of the cosmic web. Perhaps they would have sought to create a lasting monument by inducing a supernova in a specific way, or by creating a unique distribution of elements that deviates from the predictions of standard nucleosynthesis. The hypothetical field of astroarchaeology would then involve sifting through the most ancient data we can gather, not for biological fossils, but for technological ones, anomalies in the data that point not to a natural process but to an intentional act. This idea forces a radical shift in perspective on the Fermi paradox, the famous question of where all the aliens are. If intelligence can arise not just on planets around long-lived stars, but in the vast, cold stretches of time between the first light and the formation of galaxies, then the universe may have already hosted countless civilizations that bloomed and vanished in the darkness, their stories forever lost to the expanding cosmos. We, living in the brilliant light of a stable star in a mature galaxy, may simply be latecomers to a party that mostly ended eons ago. We are searching for signals in a universe that might be filled with the silent ruins of empires that rose and fell before a single galaxy had taken its modern shape. This isn't just science fiction, it is a philosophical tool that highlights the profound humility required for true cosmic exploration. As we develop new instruments to listen to the whispers of the Dark Ages, we must keep our minds open to the possibility that the signals we receive might not just be the natural songs of hydrogen and gravity, but the faint, fading echo of a presence that once called that endless night home. Ultimately, the long cosmic night was not an empty void but a necessary period of incubation, a silent workshop where the raw ingredients for everything to come were gathered and prepared. The end of the Dark Ages, triggered by the ignition of the first stars, set in motion the most profound transformation in the history of the universe, the journey from simplicity to complexity and from chemistry to biology. Each massive star, though doomed to a short, violent life, became a crucible for creation. Within their cores, the nuclear fusion that gave them light also performed the universe's first act of alchemy, forging heavy elements like carbon, nitrogen, oxygen, and iron, atoms that had never before existed. In their spectacular supernova deaths, these stars scattered their enriched ashes across the cosmos, seeding the primordial gas clouds with the very building blocks of planets and ultimately life itself. This process of chemical enrichment was the crucial bridge between the barren early universe and the fertile cosmos we inhabit today. The first generation of stars, known as Population 3, were composed only of hydrogen and helium. They could never have formed rocky planets or complex molecules. Their destruction was a necessary sacrifice, polluting the pristine environment with the essential elements for all future complexity. The second and third generations of stars that formed from this enriched gas were able to form with a full periodic table at their disposal. Around these stars, planets could coalesce not just as gas giants, but as rocky worlds with diverse mineralogies and chemistries. The universe was no longer just an expanse of light and gas, it was now filled with the potential for worlds. The timing and pace of this enrichment were critical. Had the first stars been less massive, they might not have produced a sufficient yield of heavy elements. Had reionization been too rapid or too violent, it could have disrupted the fragile molecular clouds that were just beginning to form the next stellar generations. The fact that the transition from darkness to light was a gradual, patchy process allowed for regions of the universe to remain cool and dense long enough for this second wave of star formation to occur under ideal conditions. This careful cosmic choreography ensured that the elements essential for life were not only created but also distributed widely and incorporated into new solar systems. Our own solar system and every atom in our bodies that is heavier than lithium is the direct legacy of countless generations of stars that lived and died long before our sun was even a glimmer in a nebula. This theory connects the grandest scales of cosmology to the most intimate details of our existence. The duration of the Dark Ages, the mass of the first stars, the efficiency of those early supernovae, these are not abstract parameters in a model. They are the fundamental settings that determined whether the universe could ever become a living, breathing place. A slightly different outcome could have resulted in a cosmos forever dominated by hydrogen and helium, a beautiful but sterile expanse devoid of planets and life. The end of the Dark Ages was therefore the pivotal turning point, the moment the universe acquired not just light but also meaning and potential. By studying this mysterious era, we are not merely satisfying our curiosity about the distant past. We are investigating our own origins, unraveling the long chain of cosmic events that made our existence possible, and asking the profound question of whether this journey from darkness to consciousness is a unique story or a common chapter in the grand narrative of the cosmos. We've now journeyed together through 30 of the most fascinating and mind-bending theories about the universe's dark ages, from the all-encompassing neutral hydrogen fog that shrouded the cosmos in perfect blackness to the explosive birth of the very first stars and the hidden influence of dark matter's gravitational architecture. We've ventured into the realm of the profoundly strange, from the possibility of primordial black holes left over from the Big Bang to the idea of cosmic strings, cracks in the fabric of space-time itself. This era, a seemingly empty stretch of hundreds of millions of years, is anything but a Chinese letter void in our history. It is a period rich with unsolved mysteries that challenge the very core of our understanding of cosmology and physics. It represents the final frontier of our observational capabilities, a chapter we are only just beginning to read, not with light, but with the whispers of radio waves and the subtle fingerprints left on the ancient cosmic microwave background. The most exhilarating part of this entire story is that we are living in the pivotal moment when these cosmic shadows may finally be illuminated. Our technology is advancing at a breathtaking pace, granting us unprecedented access to this hidden epoch. The James Webb Space Telescope is already peering back to the very edges of the cosmic dawn, hunting for the faint glow of the first galaxies and the chemical signatures of those first massive stars. On the horizon, a new generation of radio telescopes like the Square Kilometre Array is being constructed with the explicit goal of tuning into the 21-centimeter signal from that ancient sea of neutral hydrogen, promising to provide us with a three-dimensional map of the universe during its darkest hours. These aren't just instruments, they are time machines, allowing us to witness events that have been traveling through the cosmos for over 13 billion years, finally arriving at our doorstep with stories to tell. As we stand on the precipice of these discoveries, it's worth reflecting on what this search truly means. Unraveling the secrets of the Dark Ages isn't just about filling in a blank spot in our cosmic timeline. It is a fundamental test of our physical theories. The outcome will force us to confront the nature of dark matter, to understand the true properties of dark energy, and may even reveal new particles or forces that have remained hidden since the universe's first second. Each theory we've explored today presents a different path the universe could have taken, and soon we will know which one is written in the fabric of reality itself. This is the scientific process at its most magnificent, a grand conversation between bold theoretical ideas and precise, awe-inspiring observation. Now, we'd love to hear from you. After this journey through the shadows of cosmic history, which theory captures your imagination the most? Does the idea of a universe seeded by ancient black holes intrigue you, or are you drawn to the profound mystery of what dark matter truly is? Perhaps the notion of cosmic strings or the potential for a dynamic dark energy strikes a chord. Share your thoughts and questions in the comments below. We read every single one and love continuing the conversation with this incredible community of space enthusiasts. If you enjoyed this deep dive into the universe's greatest enigmas, make sure to subscribe and hit the notification bell so you don't miss our next exploration. Until next time, keep looking